Hello, and this is a video for Algebra 1, and this is Unit 2 notes, and we're going to be talking about linear functions. And specifically today we'll be talking about Section 1, and this is an introduction to linear functions. Our objectives today, we want to calculate the rate of change of a function, and if constant, the initial value of that function. We want to determine if a relationship is linear by analyzing the rate of change. So, what I want to talk about real quick is just a linear relationship here with the hours worked and the amount of money that you earn. And so we have this person named Michaela, and she works at a job, and what this linear relationship shows is if the more hours she works, shows the amount of money she gets paid, okay? And so let's just go ahead and kind of talk about a few things here. And before it says anything, it says determine the relationship between the independent variable and the dependent variable. Well, let's talk about what the independent variable is. Okay, remember independent variable, okay, that's your x value, okay, which in this case is hours worked, okay, which is hours. Okay, and I'm obtaining that information strictly by looking at the graph and the label on the x-axis, okay. The next one is the dependent variable. Okay, the dependent variable depends on the independent variable. This is your y value, okay? This is your y value, and that's the money earned, okay? And so, and I'm getting that information over here by looking at the label on the graph, okay? So it says, what is the domain of the given scenario? And all that is, domain is another way for us to say x value, okay? And that is hours worked, okay? If you wanted to actually put a value on it, you know that the hours worked is greater than or less than 0, okay? And then what is the range of the given scenario? Remember, range is another word for y, and that's the money earned, okay? And so then we can sit here and say that the y value is also going to be greater than or equal to 0, okay? And I just kind of know that by looking at the graph, okay? I know that the number of hours, you're not going to work negative hours, okay? And then the amount of money, okay, as long as you work, you're not going to owe anybody money, but, just for earnings purposes, you're going to start at 0 and go up. And for hours worked, you'll start at 0 and go up as well. Okay, now let's go ahead and fill in this table, and it says that the Michaela earns $8 per hour. Okay, that's good to know. $8 per hour at an after-school job. So let's kind of think about this, and we can kind of use the table as an example. If Michaela works 0 hours, then how much does she get paid? She gets paid $0. All right. And then, if she works 1 hour and she makes $8 per hour, then after 1 hour she has made $8, okay? If she works 2 hours, $8 per hour, I'm going to take 2 times 16, times 8 to give us 16. And then we'll do the same thing over here. We'll take 3 times 8 to give us a total amount earned of $24. And then, if we work 4 hours at $8 an hour, we get paid $32 an hour. So, all of these we're multiplying by 8, all right, to get what we want. And that's what you would do, if you work at a job and you get paid an hourly rate, okay? And so, and you can see these points on the graph too. All right, you can see the point 1,8. You can see the point 2,16, the point 324, the point 432, and so on and so forth, okay? But, we call that a rate of change, okay? And a rate of change is the same thing as saying slope, okay? Rate of change is the same thing as saying slope, okay? And slope, remember, is, we often call that rise over run, okay? Oftentimes, and that's what I'll call it just to kind of describe it. But really, the slope is the change in y, so the change in y divided by the change in x, okay? And so, and we'll also, to call that change, we use the, the formula y sub 2 minus y sub 1 over x sub 2 minus x sub 1, all right? And you've probably seen that before. But, in the definition here, it says it's the ratio. So the ratio, so you have a fraction, the change in the dependent variable, which is the change in the y value, okay, with respect to the change in the independent variable. So the change in y over the change in x, all right? And so then, and that's the thing here, is that, you look at that same table that we had, the hours increased by 1 each time. So all the hours increased by 1, but then the amount earned changed at a rate of 8. So this column increased by 8 for each column. And so what you do to calculate your ratio is you take these numbers and you divide them, okay? And the y goes on top and the x goes on bottom, okay? So then, you know this, all right? Michaela earns $8 out of an after-school job. The graph shows the relationship between the number of hours that Michaela works and the amount that she earns. And so if you have these different points on a graph and you connect them and you actually get a straight line, we call that a linear function, okay? And a linear function creates a line, okay? And so, but the thing that you need to see here is that it has a constant, additive rate of change, okay? And so what I think about is I think of the rise. We rise up 8 units, we go 1, so it's 8 over 1. And you can do that from every point to the next. You rise up 8 units and you go over 1. You rise up 8 units, you go over 1, okay? This is what we call a constant rate of change, all right? So and this is something that you guys do all the time, provided you have a job, this is what you guys do, and you use this stuff all the time. And the rate at which you get paid, your rate per hour, that's your slope, okay? So your slope here was 8. All right, let's take a look at the next one. And so, it's asking us, you have the scenario of you have this graph and you have these 2 points, A to B, and it wants to know what is the vertical change from point A to point B. And the vertical change is this value here on the graph, and that's a value of 1. So that's a value of 1, okay? And says, what is the horizontal change? The horizontal change is what goes across the graph, and that's this value here, and that's 2, okay? So that's 2. All right, so the change in y, change in your y-axis divided by the change in your x is going to give you 1 over 2, and that's your slope, okay? So it says, what is the rate of change? Remember, rate of change is another word for slope, okay? Rise over run, change in y over change in x. Okay, it says give the answer as a decimal rounded to the nearest tenth if necessary. So you rose up 1, okay, and then your horizontal change was 2. So your slope, and we'll call this m, is equal to 1/2, and as a decimal, that's 0.5, okay? And now you don't have to always go over and then up. You can go up and then over as well. You could go up 1, okay, and then over 2, and it gives you the same thing, all right? So that's all we're doing. Okay, the next one, it says Manuel is selling baseball caps for a fundraiser. The table shows the relationship between the number of caps sold and the amount of money Manuel has collected. So here's the number of caps sold. We'll call that our X value. And then the amount of money collected, we'll call that our Y value. All right? So it says, what is the rate of change for the given function? Remember, rate of change is another word for slope. Okay, and we think of slope, we think of rise over run. Okay, if you want to be technical, we can think about the change in y divided by the change in x. We all get the same thing. So, if I look at a table here, okay, I ask myself, okay, by what rate does the x column increase? Okay, so each of these increase by a value of 2, okay? Then the other question is all right, well, how much does the y value increase by? And the y value increases by 5 on each time, okay? So our slope, our rate of change, and I'll call it ROC, not to be confused with the movie The Rock, starring Nicolas Cage and, what's his name? Sean Connery. Okay, I digress. Rate of change, we'll just call this the change in y, which is 5, divided by the change in x, which is 2. And the nice thing is that it's constant. We keep getting 5 every time, all right? So we know it's linear, all right? So if you keep getting the same change in your y divided by the same change in your x, that's what you're going to get. So if you get 5 halves as a decimal, that is 2.5, okay? And that's dollars per cap, okay? And that's the other thing, is to be able to apply what it is that your y value is, okay? And actually applying what this says. So the amount of money versus the number of caps sold. All right, the next thing that we have to talk about is something called initial value. Okay, an initial value is the starting value of a function when the independent variable is 0. So basically what we call the initial value is the y-intercept. Okay, y-intercept. All right, and it's the y value. Okay, it's the y value. So basically the y value when x equals 0. Okay, and so on this one it says, it's that same problem. Manuel is selling baseball caps for a fundraiser. The graph shows the relationship between the number of caps sold and the amount of money Manuel has collected. How much money did Manuel start this fundraiser with? So, the idea is that you take this line, okay, you connect these points and you connect this line going all the way down, and you see that that it goes down to about, looks like 5, okay, not exactly sure, but I would say that Manuel started with $5, okay, as his fundraiser. Okay, so he already had $5, and then as he sells, more baseball caps, then the fundraiser earnings goes up, okay? So he starts with $5, all right? And this didn't work out the way as planned. I don't know why these things don't print the way that they should, but I digress, okay? We'll let you guys do that on your own. All right. The other thing is distinguishing a linear function from a nonlinear function. Now, a linear function creates a line, okay? Creates a line, okay? A nonlinear function is a curve, okay? So pretty easy to distinguish. But the difference is, you can tell off a graph pretty easily whether you have a linear function or a nonlinear function. But we do need to talk about rate of change, with a linear function. A linear function has a constant additive rate of change, okay, where you have a constant slope. So your slope doesn't change. Slope doesn't change, okay? And in a nonlinear function, the slope changes, okay? The slope changes. And this is what you do in calculus, actually, is you talk about how the slope changes over a nonlinear function. It's pretty fun. Really fun, actually. Okay, so over here it says, okay, which table represents a nonlinear function? So all I'm going to do is come in here and, okay, as x increases by 1, okay, what do the y values increase by? And these increase by 8, and then we get to this increases by 8, and this increases by 8. So this is linear, because these values don't change, okay? You have a constant rate of change, your x changes at a constant rate, so does your y, all right? So then over here, same thing, okay? Your x increases by 1 for each time, all right? And then your y values, okay, to go from, negative 1.5 to 1.5, the difference between those two is a value of 3, okay? And then to go from that to 1.5 to 3, that's a rate of 1.5. And then to go from 3 to 4.5 is also 1.5. So because these aren't the same, okay, these are not all the same, therefore it is nonlinear. Okay, this is a nonlinear function. Okay, let's check this out over here. Now, you can also have a negative rate of change, okay? As x increases by 1 on each of these, then y actually decreases by negative 3, and that occurs. So these are all the same, so this is a linear function, okay? So it's when these rates of change aren't the same, all right? Now, let's take a look at, This shows the height and distance traveled by a soccer ball, okay? So as time increases by 1, okay, the height of that soccer ball changes, as does the distance it has traveled in yards. Now let's first take a look at this table, talking about the time and the distance that it travels, okay? And so what I notice here is that, first of all, the time increases by 1 second for each time, okay? And the distance in yards changes by 17 each time, okay? And so each one of these columns gets larger by 17 for every second that it goes, all right? And so what you have here is you have a vertical change of 17 for each point, and then a horizontal change of 1. Okay, so your slope here, your m, is equal to 17 over 1. Okay, and if we do the same thing, if we want to go to the next point, we would go up 17 and then over 1. Okay, so that's 17 over 1. And same thing here, if we get to the next point, we're going to go up 17 and then over 1. Okay, so we've got 17 and then over 1. So we have a constant rate of change. This is a linear function. Okay, but let's look at something else. Okay, on the other one, all right, what we can see is that, if we took it time versus height, okay, the height here, this one increases by 5.3. Okay, and then if we go to the next one, the change from 5.3 to 8 is 2.7. Okay, so that these aren't the same. So I know that this isn't a linear function. And then it changes to, what is that? 8 to 9.8 is 1.8. Okay, and then we can see that it actually goes down by negative 2.1. Okay, and so if you look at some of these different slopes, okay, here you go up 5.3, but you go over 1. Okay, here you go up 2.7, and then you go over 1. All right, and then you go up, what is it, 1.8? I have to come back over here and look. 1.8, yeah, 1.8. So you go up 1.8, okay, and then you go over 1. And so these values are, these slopes change. And so because these slopes change, all right, this is a non-linear function. And then it even just switches directions and goes the other way. So this is a non-linear function. Okay, it's still a function, just not linear, not a constant rate of change. Okay, this is fun. I'm having a good time. All right, let's take a look at the last couple problems. On this one, it gives us this table shows the distance traveled by a car and the car's average speed on different days, okay? So you've got these different days here. You have the average speed that's calculated, and then the distance that they've traveled in miles, and this is total distance, okay? It says, given that the days are the independent variable, so this is like your x value, and here these are two different y values, okay? Which dependent variable has a constant rate of change? And so what we notice here is that, the days increase by 1, okay? Even though we start with 3, that's okay. We're just looking to see, all right, well, how are these changing? All right, and then the y values on the average speed, these increase by 3. Okay, well, that increases by 3. This increases by 5. This increases by 2, and then this increases by 3. So this is actually non-linear, all right? Okay, to figure out the distance traveled, let's do a couple of things here. Hold on. So the change in distance here is, for these two, is 165, okay? And then, so if I go 825 minus 660, I get 165. Ooh, okay, I see what's going on. If I do 990 minus 825, then that's going to give me 165. Ooh, this is fun. Okay, so we get that this is 165. Okay, this column changes at a constant rate. Okay, so which dependent variable has a constant rate of change? And that would be the distance. Okay, the distance is what has a constant rate of change. Okay, and what is the constant rate of change? And what that is that I'm taking this number 165 and dividing it by 1. Okay, 165 and dividing it by 1, but we have to put a label on this. Okay, this is a distance in miles, and this is per day. Okay, 1 day. So what we can say here is that, the car travels 165 miles per day. Okay? And that's a rate. Okay? And that's constant. Okay? I mean, you can make something happen here or say something here, but it's not going to be constant. Okay? All right. All right. Over here it says compare the different linear representations of Rex's and Max's growth as puppies. Okay, which puppy grew at a faster rate? And who doesn't like puppies? We all like puppies. Okay, and then which puppy weighed more when they were born? Okay, so on this one, okay, every week, okay, the number of weeks we can kind of tell who's growing at a faster rate. And so what I have here is that, okay, as we increase by 1 week, okay, how much does the weight increase by? And so this increased by, what was that? Is that 2.5 pounds per week, and then another 2.5 pounds? So on this example, this is 2.5 pounds per week, okay? That's the rate for Rex's growth. Now let's look over here. And so, all right, so here I'm going to go up, oh dear. All right, I'm going to draw a little triangle here, see if this works. I'm going to go up 8.2 minus 5.7. All right, so the vertical change is 2.5, and then a change of 1 week. Okay, same thing for the other one. 10.7 minus 8.2 to get that value is also 2.5, and then change of 1, and so on. All right. So this one is actually the same thing, 2.5 pounds per week. Okay. So which one grew at a faster rate? Neither of them grew at a faster rate. They had, the same amount of that they were going by. But it wants us to know which puppy weighed more when they were born. So if I wanted to figure out, okay, well, what happened on week 1? Okay, how much after they were born for a week? How much did they weigh? And so if I take 11 minus 2.5, that's going to give me 8.5 pounds. Okay, 8.5 pounds. And then at week 0, if I go backwards, subtract another 2.5 from that, and that's going to give me 6. Okay, so Rex weighed more at time 0 as an initial, when they were born versus Max. Okay, but they grew at the same rate, 2.5 pounds per week. Okay, hopefully you enjoyed this, and we'll talk more about slope and such as and all that good stuff. I've had a lot of fun. Hope you had too. See ya. Bye.